Hello, this is Syaroh, and here is my final report for Senior Mechanical Lab. First of all, this experiment is an integrated experiment that combines three modules into one experiment. The modules are including thermodynamics, fluid mechanics, and heat transfer. The objective of this experiment is first, able to apply principles of thermodynamics, fluid mechanics, and heat transfer in the experiment. Second, able to design and assemble the experiment setup, and the last one is able to do analysis on the result. So, before the experiment began, there are a lot of preparations that have to be done. The first one is the experiment preparation about the setup. So here is the setup of the experiment. The siphon here, along with this pressure gauge and a valve, will be the fluid mechanics experiment. And then boiler here until the pump and also this reservoir will be the thermodynamics experiment, while the heat transfer experiment will be about the temperature changes in here. So for the detail, it is in the next slide. So here is the detail of the design. The first one, this is the boiler design made of kettle and also pipes. And here the setup design for temperature and also the pressure gauge. Here is for the siphon, and here is for the generator or the pump set up in the thermodynamics experiment. So the next experiment preparation is about the shipping plan. So this shipping plan will become the consideration on building the setup. So in the first scenario, there will be three setups built and one setup for each experiment. Then each setup will be handed over to the next member that will do the experiment, and so that the total shipping cost will be 195,000 rupiah. In the second scenario, there will be no shipping cost because each member will build his own setup. However, the building expenses will be very expensive. And the last scenario, it has no shipping cost, but the setup building cost will be less than the scenario 2 because there will be only one setup that built for all the members. And here our group choose the scenario 3 because it is the most suitable for us. After choosing the shipping plan, the next step is components purchase. So here are the list of the components that we'll purchase, and the total expense and this purchasing is about 579,945 rupiah. So after the preparations done and all the components are ready, the next step is assembly. In the assembly, the parts are assembled based on the design, of course. And the first assembly is the boiler. Here is the boiler assembly, consists of a kettle, L joint, and also the pipes. The next is the temperature gauge. Here is there is a T joint, and also here is the temperature gauge. The next is heat transfer. Here is the T joint, and also there is a copper joint here, pipes, and also here is the pipes for the cold reservoir. And the next is the siphon assembly, consisting of pipes, L joint, and also the T joints for the pressure gauge, and also the valve. So the last one is the generator assembly. here is the pipe, L joint, and there and also the generator itself. So here is the experiment module for thermodynamics. This setup is able to show that the heated vapor able to produce work by turning the turbine, which is related to the phenomenon of Rankine cycle. The temperature of the steam can be measured using the temperature gauge, and also the effect of temperature can be seen on the brightness of the lamp, which indicates the work input. The next module is the fluid mechanics. This setup is able to show that the pressure that is exerted by a fluid at equilibrium at a given point within the fluid due to the force of gravity phenomenon of the hydrostatic pressure. The pressure of the fluid can be measured using the pressure gauge, and the pressure that is displayed by the pressure gauge can be compared with the calculated pressure using Bernoulli's principle. The last module is about the heat transfer module. The setup is able to show the reducing temperature of vapor, which is the phenomenon of heat transfer, and the difference in the temperature before and after the steam passes cold water can be measured using the temperature gauge. And the last one is the heat transfer rate, and the resistance in the copper joint can be calculated. So after the experiment, here is the result of the thermodynamics. The experiment is based on the Rankine cycle, or the work that produces by steam, which based on the temperature of the steam will expected to generate electricity. However, after the steam reach a temperature above the boiling point of the water, the LED bulb is still off, which is the unexpected result. And then the cold water from the cold reservoir is on. This is to help generate the electricity. However, as you can see here in the red circle, the LED bulb is still off. So to know what's happening in the generator, here is the calculation of the power generated by the generator using the formula of W dot per M dot equals to H1 minus H2, where the W dot is the power generated, the M dot is the mass flow rate of the water, the H1 is the enthalpy of the steam at the generator inlet, and H2 is the enthalpy of the steam at the generator outlet. So the calculation is based on the steam temperature of 100 degrees Celsius. It is in the generator inlet, and also the assumption of the steam temperature at the generator outlet, which is equals to 99 degrees Celsius with the mass flow rate of 1 kilogram per second. And this data of the enthalpies are taken from the thermodynamics table for steam. So after some calculations, the power generated in the generator equals to 1.9 kilowatt, which is a big value. But why is that the LED is not on? So here is some predicted reasons on why the LED bulb is off. The first is maybe the steam is not hot enough. And also the second, the generator is not for steam. And the third, the water flow is not powerful enough to turn on the LED bulb. And maybe there are some mistakes in the setup. And the last one is maybe there is a wrong assumption in the calculation. So the next result is about the fluid mechanics result. This experiment is finding pressure at the particular position. The pressure is found using the Bernoulli's principle. So here is the Bernoulli's principle. And knowing that this is the first position, this is the second position, this is the third position, and the second position is the pressure that we would like to know. So here is the set of the parameters, and also using the Bernoulli's equation, the value of the velocity at the third and also the second position is known, which is equals to 4.43 meter per second. Using this value, the pressure at the second position can be known. Also using the same Bernoulli's equation, the pressure at the second position is minus 0.05 atm. And from this calculation, the value of the pressure is negative, while the pressure gauge used in the experiment is a positive pressure gauge, and therefore the pressure gauge cannot read the pressure of the water in the siphon. So not only in the calculation, the negative pressure is also shown in the real experiment. So here is in this picture, this curve is showing that there is a positive pressure in the siphon. It is when the tap water is fed in the siphon. However, when the tap water is not fed anymore, or when the water from the high reservoir already falls and also flow in the siphon, the pressure inside the siphon becomes negative. This is shown by the curve that is not in here anymore. Moreover, due to the velocity of the water in the siphon, there is an additional experiment, which is installing the generator in the siphon. And from the experiment, with the velocity of the water equals to 4.43 meter per second, the generator has succeeded in generating the power and turning on the lights in the LED bulb. So in the red circle here, we can see that there is a slightly green color in here, which means this LED is on. And to make it clear, here is the color of the LED bulb when it is installed in the water siphon. So last but not least, here is the result and also the analysis of the heat transfer experiment. In the experiment, the copper joint is illustrated like this. So it is a cylindrical object which has a hollow where the hot fluid or the hot steam is flowing through, and also it will be showered with the cold fluid, or here is the cold water from the cold reservoir. And analyzing the heat transfer in the copper joint, there will be two results, which is the heat transfer rate and also the thermal resistance of the copper. Using this set of the properties, the heat transfer rate in the copper joint is calculated, and the result is minus 30.45 kilowatts. The minus sign here means that the heat is transferred from the hot water or the hot steam to the cold water. Also, the thermal resistance of the copper joint is calculated, and the result is 2.76 times 10 to the minus 3 kilo per Kelvin per watt. As for the conclusion, this experiment activity has met its objectives, such as able to apply principles of thermodynamics, fluid mechanics, and also heat transfer in the experiment, and able to design and assemble the experiment setup. There are a lot of lessons learned during this class, such as able to do hands-on work, do the technical presentation in the beginning of the class, solving the expected and also the unexpected problems during the assembly and the experiment, and most importantly, able to analyze the result. The last but not least is the feedback. Um, for me, the class is fun, especially the preparation before the experiment began. However, when the experiment is on progress, it is very challenging due to the unexpected problems, such as the setup problems that suddenly occur, which needs to be fixed. Other than that, this class has given a lot of benefits, such as hands-on experience, sharp problem-solving skills, along with the basic technical skills and others. As for the suggestion, it will be very good if the campus can provide the setup and also the model, so that there is a fixed standard for every student to do the experiment. And that's all for me. Thank you for watching.